Okay, let's talk about hashes, the Merkle tree, and mining, and how it all fits together. It's important to understand about that hashes, again, like we said, they're unique identifiers. They can be tied to a specific transaction statement, right? They can't be tied back, and knowing one transaction statement doesn't give you any more information about knowing the second or third. So I'm gonna go straight to this slide because I think it starts to explain it. So while one input always represents one output, we can do something called blending hashes. So what I mean by that is, let's say we take these top three inputs, right? The circle with a dot in it, and the square. We can create a hash of each one of those, right? Now this is just an example of a hash because a real SHA-256 hash would be much larger and be in a hexadecimal format. But we can take these three hashes and we can essentially hash them together to get this summary hash of these three. And we can do the same thing with the bottom two hashes. We can hash them individually and then hash them together to get this summary hash. And then we could take these two hashes, the top summary and the bottom summary, hash them together to get this, this summary hash. And so if there's any change that's made to any of these inputs, right? So let's say I took this little dot out of the center here, it would radically change this hash, 46271, which would radically change this hash, 83513, which would radically change this final hash. So if there were 100 copies of this blockchain and they all had the most recent block hashed, and my hash was different than everybody else's, everybody would realize that my copy of the blockchain had been corrupted and they would all reject it, right? And that's how this is used in blockchain. Now, this relationship of hashes from here to here is what's referred to as the Merkle tree. So in a blockchain, if each one of these, if each transaction is run through a SHA-256 generator and is hashed, right, the block essentially has the hashes of each of the transactions, which I can hash together into this one summary block, right? And then what I can do is I can take, so let's say in this very first Genesis block, I take all of the transaction statements, I create a hash of them, I create a summary hash of the whole block. I can embed that into the second block. And in the second block, I can take all of the hashes in the second block, blend them together along with the summary hash from the previous block, blend all of that together, get a new hash, and drop that into the third block. In which case I'm going to have all of the hashes of the transactions in this block along with the summary hash of the last block, create a new hash, and that'll go into the fourth block. You're probably starting to see the pattern here. And that way, if anybody makes a change to any transactions anywhere in this chain, right, it will become immediately available to the most recent block, or become immediately identifiable that there's something wrong with this block. This block is out of sync with all the rest. So really the purpose of the previous hash is a couple things. One is it saves time. So when a newcomer comes onto the network, they actually don't need to download everything in history. All they need to do is download the most recent block. It saves disk space. You don't need blocks prior to the latest block, since the latest block has a mix of all the previous blocks. Now, let's go a little deeper. So here are each of the blocks. They have the transactions of all the transactions in that block. They have that hash that's put into the subsequent block, which is done here and here. Now, in addition to the hash of the previous block and the summary of all of the transactions, it also has a date timestamp, and it has one more thing. It has something called a nonce. Now, what is a nonce? Well, we talked before about what the miners do, right? The miners have to solve a computational puzzle, right? And so here's how they do that. They guess some random value and they put it in the nonce. And they hash the block of the previous block, the summary of all of the transactions, the date timestamp, and this nonce. And when the miner takes these four inputs and runs them through a SHA-256 generator, they're going to get some random set of numbers and letters, A through F and 0 through 9. Now, here's how they win the contest, right? And then when they win a contest, they get a block reward, and their block gets added to everybody's blockchain. But here's how it happens. There's a rule set that says if the miner has 4 leading zeros when they hash all of those things together, then they win. Now, remember, any character in a SHA-256 output can be either an A through F or a 0 through 9. So what's the likelihood that all 4 of the first 4 characters would be a 0? Pretty low odds. So then they'll guess again. What's the chance? Still pretty low. They'll guess again and again and again and again and again until finally they'll put some value in the nonce so that when all 4 of those things are hashed together, the first 4 digits of the output will be 4 zeros. And at that point, figuratively, that computer raises its hand and it says, hey, I figured it out. If we take all of these transactions, the previous block, we take the date timestamp and this nonce that we just guessed is ABC 123, and you put all these together, the output is going to start with 4 leading zeros. And remember, it's very difficult to guess, but it's very easy to check. When the rest of the computers, at least more than half of those computers, verify, they said, yep, when I put those 4 numbers in, I get an output that has 4 leading zeros. Yep, check, 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 I agree. When over 50% of them agree, then they'll say, okay, it passes. Let's all take a copy of this block and add it to our copy of the blockchain. And now all of the blockchains have been updated with the most recent copy. That happens every 10 minutes. And if somebody's trying to falsify the system, or they're trying to guess and check, they would have to do it in less than 10 minutes, because 10 minutes from now, that next block is going to be added, and it's going to completely change the dynamics. It's going to, because now you'll have a new summary hash to deal with. So I hope that that's clear. I know that when I teach this in person, it's a challenging concept to get, so I can only imagine what it's like to get on the other side of the video screen. But there's one other thing I have to share with you. So remember, I said that a Bitcoin blockchain is going to mint a new block about every 10 minutes. Well, how can you assure it's going to be 10 minutes when this is all about guessing? And somebody might guess the right answer in 1 minute. They may not guess the right answer for 30 minutes, right? So how can you say it's going to happen every 10 minutes? It's based on statistical probabilities. So given the number of miners that are competing, right, given a number of factors, the difficulty level will be increased or decreased so that statistically the average of block time is about 10 minutes. So some will be more, some will be less. Now you're asking, how do you adjust the difficulty level? If it's based on everyone guessing and checking, and they have to get 4 zeros, then how do you make it easier or harder? Well, the number of leading zeros is what determines how difficult or easy it is. So if it's taking longer than 10 minutes, right, then the protocol would automatically make the guessing easier. And they would make the guessing easier by making it, instead of 4 zeros, make it 3 zeros. Right? Or if people were solving the challenge in less than 10 minutes, maybe on average 8 or 9 minutes, then it would add a 0 to the first 4 leading, so it'd say that it would have to be maybe the first 5 leading zeros, right? And then that would make it more difficult. So the difficulty of the nonce challenge is changed based on the statistical probability that the solution will be arrived in about 10 minutes. And that's a little bit about how that works. Now, one more thing that's not on the slides is a little bit about the ecosystem, because people are always talking about energy. Here's the thing. Energy is not uniformly available. In some places it's scarce, and in other places it's abundant. There's some places where there's an excess capacity of energy, right? And so And so that's going the amount of energy, the price of energy, those things are going to impact whether or not miners actually decide to turn on their mining machines or turn them off. Another thing that will impact it is the price of Bitcoin. Because when a miner solves a challenge and their block gets selected to be added to the blockchain, that miner is rewarded. Today, I think it's 6.25 Bitcoins, right? So if the price of Bitcoin is very high, there's a big economic incentive for people to mine because periodically, occasionally, if they crack the code, if they win, that 6.25 Bitcoins is very lucrative, right? Now, if the price drops and the price of electricity goes up, well, a lot of miners will drop out of the mining pool, right? And if a lot of miners drop out of the mining pool, the difficulty level will be adjusted down so that statistically there's a likelihood that a block will be added every 10 minutes. Another thing that will determine whether or not a miner is going to participate is the age and efficiency of its equipment. So a lot of Bitcoin mining machine companies, they will be introducing new, faster equipment on a regular basis. Well, if you're competing with other miners and they have equipment that's mining Bitcoin at a faster rate than you are, right, or guessing and checking at a faster rate, your likelihood of winning diminishes. And if your likelihood of winning diminishes, you're probably going to make less money. And if the price of Bitcoin is low and you're not winning because you have an older machine, right, that's just not as fast as the newer machines, these are some other factors that would cause you to turn your machines off. So the price of Bitcoin, the cost of energy, the speed and capability of your machine, and the difficulty of the protocol, all of those things combined create a self-regulating environment. So it's really fascinating. All right. Now, the blockchain and the nonce and the hashing and all that stuff, all that does is tell us whether or not we can trust the blockchain. But remember, all of those transactions are hashed. So we can't read them. We can't use this to determine how many Bitcoins are in a particular address. For that, we have something called the transaction database. And what the transaction database does, it technically doesn't use the term addresses. Technically, it uses the term inputs and outputs. But I'm going to use addresses just to kind of keep it simple. And what this transaction database, the way it works is, it says if you have, and again, I'm going to call it address. Technically, that's not correct, but hopefully it makes sense. And let's say you have 20 Bitcoins, and you want to send 5 of them to me, right? The protocol for the transaction database is that any address can you can't have a partial quantity in there. Meaning, if I have 20, I'm going to send 5 to you, and I'm going to send 15 back to me. It's going to come to a new address, right? But the transaction database will have the balances and amounts of each. Technically, it's not called an address. Technically, it's called an output of each output. And that's connected to the blockchain so that when you go to do a transaction, you'll go to the blockchain, you'll see the transaction database. The blockchain will tell you whether or not you can trust it. And if you can trust it, then you'll know how many Bitcoins are in that particular address if you have the key to be able to read it. Right? And then a wallet, we'll talk about this more a little bit later. A wallet is essentially your doorway to be able to read the transaction database and be able to write to it. Basically, sign a transaction that says, I'm sending some person 3 Bitcoins. So you can actually send that to the transaction database, and you can sign it. And then once that happens, the blockchain is replicated across the network. There is consensus. And the idea that you have to have over 50%, there's this concept called a 51% attack. If you held 51% of the network, there's a potential that you could essentially create a false picture of what's been agreed. All right. This is generally hack proof because, like I said, with Bitcoin, it's going to change every 10 minutes. It's going to be very difficult to hack this solution. And it's important to understand, and I've mentioned it a couple times, but I can't mention enough. Blockchain is a protocol. There's a lot of different protocols. When we talk about blockchain, we are oftentimes referring to things that are similar to the Bitcoin blockchain, although there are many variations, which we'll cover in a subsequent module. But these protocols, essentially, just like the internet uses HTTP and TCP/IP, it's a set of sort of language, it's instructions to allow computers to participate in a blockchain solution. All right, and I think that's it. So on the next module, we'll talk about what some of these different protocols are.